in Sloan. He is a new assistant professor in the ME department. He just started this fall. So Dan is, of course, also one of our own in the sense that he is a graduate of university. He studied under Ram Vasudevan. And thereafter, he went for a postdoc with Rob Wood at Harvard for 2 years.
3 years.
3 years.
Mhm.
Okay. And then we got him back. So we're happy to have him, and I'm looking forward to talk today. Thanks.
All right. Thanks, Brent. Brent was on my PhD committee, so he has a hand in some of the work that you're going to see today as well. So yeah, hi everyone. For those who know me and those who don't, I'm Dan Bruder, new assistant professor here. And today I'm going to talk about work that I've done in the past on using data and Koopman operator theory to try to make soft robots more capable and easier to control. So to start, why should we care about soft robots? If you're, the robots that we're most familiar with seeing most of the time are things like this. They're strong. They consist of rigid links and heavy motors, and they're fast, they're accurate, they're precise, which is all things you really, really want to have for a robot that's building your car. These industrial applications where we want high precision. But those same robots, if they malfunction in the presence of a human, have the potential to cause serious harm and injury. So practically speaking, in these industrial settings, we physically separate the robots from the humans so that things like this don't happen. But of course, if we want to get robots to help us in our day-to-day lives and automate things outside of the factory floor, we need them to be able to safely operate side-by-side humans. And so again, if we take a rigid-bodied robot that has low backdrivability and we try to do a task like feeding someone, for example, if the robot has a perception or a control error, it has a potential to injure the person that it's trying to help. And so a different way of constructing robots could be to make them out of soft materials that are compliant so that even in the event of catastrophic controller failure like this, you don't have to worry about the robot causing serious harm to the person that it's operating with. So safety is one big, potential application for soft robots, but that's just, scratching the surface. There's also a lot of tasks that compliance is helpful with that soft robots have the potential to do better than rigid-bodied robots. So beyond just interacting with humans safely, they can do things like navigate through their environment through, physical touch, things that we usually try to avoid with heavy rigid-bodied robots. They can absorb impact without taking damage. They can conform their shape to various geometries in their environment to do things like grasp a bunch of different objects without any difference in their controller. And then they can more easily mimic the types of continuous morphologies and motions that you see in biological systems like fish and snakes. So with all these potential benefits out there, why don't we see more soft robots in our day-to-day lives? And I'd argue probably the biggest reason is that they're really difficult to control. There's a few reasons for that. So one of them is that rather than having their deformation localized at joints the way we do with traditional robots, their deformation is distributed across their body. So they have this continuous shape. And so that makes it hard to easily parameterize what their shape is with just one or two numbers or one or two joint angles. And because they have this continuous deformation, they have essentially infinite degrees of freedom. So you're always going to be under-actuated in that case because you can't have infinite actuators in your system. So that presents another challenge. And then they're made of these soft materials that you can't make the rigid body assumption that we typically do when we're controlling mechanical systems. You have to account for nonlinear material properties. So those are the reasons why it's challenging to model and control soft robots. And so the approach that I'm going to talk about today is a data-driven approach to try to make it easier to get a handle on these systems. And so the benefits of this approach is that it allows us to construct accurate linear representations of the dynamics. And these are global linear representations, not just linearizing about a single equilibrium point. Because these models are linear, it lets us use efficient linear control methods on them. So it enables us to do real-time feedback control or real-time optimal control. And then we'll show some extensions of this where we can accommodate loading in our models. Again, this is something that is not too hard to do because we have this linearity of our model. And it's nice because it applies, because it's data-driven, it applies to really arbitrary dynamical systems or robots. But in our case, it works for soft robots that have different types of morphologies. Although in this talk, you'll see mostly it applied to trunk-like manipulators like this one. Okay. So that's what I'm going to talk about today is the Koopman approach to soft robot model. So I already talked about why soft robots are difficult to model from first principles. So it's hard to construct physics-based models of them. But they're actually particularly amenable for data-driven methods. So one reason is that it's relatively safe to collect data from them. So you can command a soft robot like this one under randomized control inputs with minimal risk to damaging the robot or your surroundings. So in other words, like collecting data is cheap, where if you imagine trying to collect data from an autonomous vehicle, for instance, by just letting it run randomly through the town, it wouldn't be as safe to do. Another thing that's beneficial is that this lets us avoid making the simplifying assumptions that we typically have to make with physics-based models that will make our physics-based models tractable, but then also not as accurate for the particular system we're trying to model. And then it's really important for these type of soft robotic systems, which are typically handmade in the research lab by tired grad students, and they tend to have fabrication defects that make two robots that are supposed to be the same actually behave somewhat differently because their dynamics are affected by those defects. But with data, you're learning the dynamics of the system itself, and so even if you have these fabrication defects, the data-driven model can account for those. So these are why soft robots are amenable to data-driven techniques. But of course, not all data-driven models are great for control. So we can get accurate predictions from data-driven models, but for control, we actually want more than just accurate predictions. And so when I think about my ideal control-oriented model, there's two main traits I want that model to have. The first is that it's accurate, because if your model's not accurate, well, what's the point, right? You want to have it make good predictions. But secondly, I want my model, if at all possible, to be linear. Because like I said earlier in the talk, if I have a linear model, then I can use off-the-shelf efficient linear control methods like LQR, MPC, in order to control my system, rather than having to resort to nonlinear control methods, which are usually less computationally efficient for most systems. So if I had my system and I said, you know what, I really just want to have a linear model. I don't care about anything else. I could get a linear model from data. I just take data and I just do linear regression on that data and fit the best linear model I can to it. In that case, I'd have a linear model, but if the underlying dynamics of that system were characteristically nonlinear, I'm unlikely to get a very accurate model outside of maybe a neighborhood of an equilibrium point or something like that. So I could go the opposite direction. I could say, okay, don't care about linearity. I just want to get the most accurate predictions possible for my model, right? And so, we've seen that with deep learning and training neural networks, it's possible to make really good predictions for many systems, right? If you have enough data, you can represent almost arbitrarily complex patterns with neural networks. But then, of course, you're sacrificing that linear structure. The neural network is not generally a linear object. So the real strength of the Koopman-based modeling approach is that what you get in the end is something that is accurate, or at least in the examples I'll show, you can get accurate predictions from them. But you still get this linear representation of your system. And so it sort of combines the two things that I really want in most models. So how does this actually work? I think it's actually, before diving into the definition of what the Koopman operator is, I think it's useful to think about it conceptually, what it does for us, using an analogy from machine learning. So take, for example, the case where we're trying to classify unlabeled data points, okay? And we have a set of labeled data points to sort of train our classification on. And if it's the case where I have a set of data points like this, where some of them are labeled red, some of them are labeled blue, if they're distributed the way I've shown it here, I could separate them by a line. So I could draw a linear boundary in my feature space, and so my classification algorithm can be written as a linear program, which is great. It's efficient, easy to implement. Okay, but now let's say that my data points are distributed differently. So now they look more like this, where I have red points concentrated in the middle, and I have blue around the outside. So now there's no single line I could draw that would separate the red and the blue points. So I could either draw a bunch of lines and take the intersection of them, or I could draw a circle boundary, which is a nonlinear boundary now. So in this case, I can't write this as a linear classification algorithm, which is a bummer because I really like linear algorithms. They're nice and easy to implement. So the idea is that we can take this set of data points, and by lifting it into a higher dimensional space, we can recover a representation of that data that lets us draw a linear boundary between the data points. So in this case, I define a third dimension for these points as x squared plus y squared, and that puts all my points on this paraboloid, or paraboloid in 3 dimensions. And now, if I want to separate the red and blue points, I can do it with a plane, which is a linear constraint in the higher dimensional space. So I'm back to being able to use a linear program to classify my data points. So the idea here is that by increasing the dimension of my space, I can get a representation that is better for the task that I'm trying to achieve, which in this case is classification. So the Koopman operator is the same idea, but applied to dynamical systems, where I start out with a nonlinear dynamical system in my state space, and then by lifting it into a higher dimensional space, I can get a version of that system that can be described by linear dynamics. So I can describe that flow with a linear system. Okay. So now what actually is the Koopman operator, and how does it do this for us? So to see that, consider just an arbitrary nonlinear dynamical system, which we can represent those dynamics with a continuous ordinary differential equation, or the discrete flow map, which basically takes states, flows them forward one discrete time step at a time. So if I plot a trajectory of this system starting from my initial condition x0, I flow it forward one time step, and I can do that repeatedly to build up a trajectory of that system in the state space. Okay. So now let's introduce the Koopman operator. The Koopman operator is also called the composition operator because the way it's defined is that it takes functions defined over the state space, in particular scalar valued functions, and it composes them with the flow map of the underlying dynamical system. Okay, so that's what the Koopman operator does. The operation composes it with this phi function. So visually, what that looks like is if I have some, in this case, real valued function f defined over my state space, and I evaluate that function at my initial state, if I apply the Koopman operator to that function, it gives me the value of the function one time step later along the trajectory of the underlying dynamical system. And so if I repeatedly apply that Koopman operator, this is a linear operation, I can basically advance the value of this function forward in time. And if I know the relationship between that function and my original state, I can recover my actual predictions of the state forward in time. So in this way, it lets us advance the value of our state through a linear operation. Okay. And so I showed this example for a system with no control inputs, but it can also be applied for systems that do have a control input. Just typically the assumption we make is that the control input is held constant between time steps. So that's just a caveat there. Okay, so the question you should be asking now is, okay, if you're telling me that I can take any nonlinear system and represent it with a linear system, like, doesn't that solve all of controls? Like, can't we just do everything linear? And the answer is no, because this definition of the Koopman operator assumes that it's a infinite dimensional object. So functions are vectors, but they're infinite dimensional vectors. The Koopman operator is an operator that acts on functions. And so it's infinite dimensional, and in practice, we can't carry around an infinite dimensional operator. So we have to approximate what it does on some finite dimensional subspace. And when we do that, we can represent it as a matrix, like any other finite dimensional linear operator.
Are there
Yeah.
results in the control input case on existence of infinite Koopman operators?
So so in the non-control input case, there's literature that shows that as you increase the number of basis functions, you converge to the true Koopman operator. With the control input, as far as I know, it's not there's not a proof. It's we think it's probably going to work, and then we show that anecdotally that as you increase the number of basis functions, you're able to get convergence to like trajectories of the system. So as far as I know, unless there's something new in the literature, we don't have the convergence proofs for the input case, but we do for the autonomous case. Yeah.
Another quick question. So
Yeah.
even in the autonomous case, what I remember is that you have to assume that you only have one omega set. So your system can be nonlinear, but you can't have like two equilibria, otherwise your Koopman node is going to blow up, right?
Yeah.
That's
a- Yes, so multiple equilibria.
Yeah, multiple equilibria. So if you do the
Yeah.
Koopman nodes around one, then it blows up around the other one, basically.
Yeah, I think I think that the way that that's usually handled is you actually have to learn different Koopman representations around different equilibrium points if you have multiple. What paper? I think, yeah, there's a paper by Brunton or Mezich that talks about that. Yeah, so you're right. Yeah, in the case when you have multiple equilibria, you have to, there's some caveats to this. There's lots of caveats to this. Go ahead.
I think there is a theoretical proof of like Koopman operators existing for all systems so long as like the control input acts bilinearly on the system. Are you making any assumptions here, underlying assumptions of how the control input acts on the system?
Oh, so I'm not making any assumptions here. It is true that you can show that if you have a nonlinear system that is control affine, then there is a bilinear Koopman representation. So in the lifted space, you have a bilinear dynamical system, not necessarily linear. So for the control input case, actually, I should say there is an assumption here. For the control input case, to get a linear model out of it, we're assuming that the input is showing up in our lifted state as itself. So we're not lifting the control input. If we want to get a linear time invariant, like, control system in the end. Now you can, if you don't, so we'll see that there's a way that you can use Koopman to actually do nonlinear system identification, where you don't actually care about doing control with the linear part of it. You just want a nonlinear system, and you want to use linear regression to find it. In that case, you can lift the control input. So it can show up in your basis functions as a bunch of nonlinear functions of the input, but then you don't have the linearity of the input in the lifted space. Yeah. It's good questions. So yeah, we'll see that a little bit. Any other questions before I go on? Okay. So, all right, so in principle, we have to approximate the Koopman operator in a finite dimensional subspace. And so, a way to do that is basically we choose a finite set of basis functions to define a subspace that we're going to define the Koopman operator over. And then once we have the set of basis functions, we can represent any functions in that subspace as a vector, right? It's a weighted sum of all of these basis functions. So we can represent it just as a vector of coefficients. And likewise, we can represent the Koopman operator as a matrix. So this is the definition of the Koopman operator from the previous slide. I replaced that with this new matrix vector notation. And what we see is that this holds for any vector in the space, so we can actually cancel C from both sides. And we end up with this equation, which basically says that the transpose of this Koopman matrix, this finite dimensional Koopman matrix, will flow the value of the vector of all basis functions forward one time step. So essentially, this Koopman matrix acts as a discrete flow map on a lifted state, where that lifted state is a vector containing all of our basis functions evaluated on the lower dimensional state. Okay. But of course, I mean, this is also, it's approximate because we've restricted it to a finite dimensional space. So that's the idea, but how do we actually take a real system and then identify a Koopman operator for it? So to walk through those steps, I'm going to use this example of a soft robot, which consists of these two bending segments, which are controlled by three pressures. So these are pneumatic actuators. So there's three pressures that go in to determine the motion of this robot. And then the output is the position of a laser dot, like this one, on a sheet mounted below it. So we have like a three-dimensional input space and a two-dimensional output space. And so the process goes like this. We start by collecting data. So we have a set of sort of like randomized linear interpolated control inputs, and we measure the input and output of the system over a bunch of data points. Then we take that data and we lift it into a higher dimensional space spanned by a set of basis functions of our choosing. So in this particular case, we used monomials up to degree 2 as our basis functions. And then we appended the input to the as like sort of the last M set of basis functions. And this speaks to your point. We did that so that in the end, we end up with a linear controllable system. I shouldn't say control, but a linear system with the control input where we want it. And so I'll use a shorthand Z to be the vector of all of these non-input states. So then once we have those lifted data points, what we can do is we can identify this Koopman matrix through just linear regression. So we find the matrix that best describes the one-step transition between consecutive lifted data points over the whole set of data points. And we just end up with a matrix that looks like, something like this. And so I can either take that matrix and decompose it into an A and B matrix so that I get a linear time invariant system of my lifted state Z. Or if I want to, I can also project it back down into the original state space, and I end up with a nonlinear representation of my system as just a weighted sum of the basis functions. So even if I'm not interested in doing linear control, this is a way of doing nonlinear system ID without solving a nonlinear optimization problem.
You had a naive question. So at the beginning, you kind of gave this nice trade-off of like linearity versus accuracy.
Mhm.
And you discarded neural networks because they're not linear.
Mhm.
At the end of the day, it's nonlinear in the state, linear in the input. So what if I just said, what I want is linear in the input? Are you actually like, is the fact that it's, how should I phrase this?
Yeah.
If I had just said x of k plus 1 is some function of x of k plus b times u,
Yeah.
it's nonlinear in the state, but affine in the input.
So you could certainly do that, but for doing something like model predictive control, we're trying to optimize over a finite horizon of states and inputs. We actually use the linearity in the states as well as the linearity in the inputs to do that.
But it's like a hidden
Efficiently.
linearity, I guess, right? Because the states are not, all the entries of Z are not independent of each other. And maybe that'll become clear in the rest of the talk that like,
Yeah, okay, yeah, that's right. That's right. All the entries of Z's are not independent of each other. That's right.
so when you're gonna do like MPC on the state, but the states
Yeah.
are not evolving in the same way as like, it's not a linear system in the sense of like, if I would normally write it out, all the states would be independent
Yeah.
entries of each other.
Yeah, so right. The MPC doesn't know that there's a dependence between the different states. So it's just, assuming that all the states are independent. But of course, as your Koopman operator is not, your finite dimensional Koopman operator is not perfect. So when you're advancing the states using that Koopman operator, there's no guarantee that the relationships between states is preserved. And in fact, it's almost never. So that's why we have to, plan over, short enough time horizons, because we know that we're basically leaving the manifold of legitimate lifted states anytime that we apply the Koopman operator. So that's true. But again, it's we kind of think about it the same way with any model. When we do MPC, we know the model is not making perfect predictions, and the case is here too. So we take the first few inputs and then we replan, and that seems to work. Yeah.
That last point you mentioned, was that alluding to like the problem of closure in the context of like Koopman representations?
Which,
On the Koopman operator, like you assume like your set of basis functions, they form like a subspace that's such that when you apply your Koopman operator, you're not leaving the space in which that operator applies.
Yeah.
Or is valid. Is that what you're referring to with?
that's basically what we're talking about here. Yep, exactly. So, in general, you don't have, there isn't, or you can't find a finite dimensional approximation of your Koopman or a finite dimensional version of your Koopman operator. The exception is that sometimes you can find a finite dimensional invariant subspace, so that, like you said, when you apply your Koopman operator, you don't leave that space of functions. But I didn't enforce that here, or it's a challenging problem to find the Koopman invariant subspaces. And as far as I know, no one's shown like a constructive way to always do that. Even if most systems have a finite dimensional. I think it's certainly true that most systems do not have a finite dimensional Koopman invariant subspace, but there's some examples in the literature of ones that do to illustrate that. Yeah. Okay, so this is just to show, so if we took the system and then we showed the predictions of the linear Koopman model and the nonlinear Koopman model over a 6-second horizon. And so you can say that, qualitatively, we're getting, similar motions to what the robot's actually doing, which is shown in gray. But likely for the reasons that you specified, we're not getting, perfect predictions as the horizon gets longer. But if we compare that to a state space model that we train on non-lifted data, so we basically just do linear regression on the non-lifted data, the Koopman model does better predictions. And then, we also compared it to a neural network model. And while this certainly doesn't represent the absolute best case scenario for neural network models, we know that by tuning hyperparameters and changing layer depths and things, you can get better models than probably what's here. We, found that even in trying different types of neural network constructions, our nonlinear Koopman models were pretty comparable in terms of prediction accuracy and better in many cases. So that's just to say, like, these models can generate accurate predictions that are on par with other methods. But like I said, like the true benefit from a control standpoint is not just that they give you predictions. There's lots of ways of getting models that give you good predictions. It's that they give you a linear representation. And so we took this model and put it into a receding horizon model predictive controller to control this robot. And so, for anyone who isn't familiar with MPC, basically the way that works is at each time step of the system, we're measuring the current state, in this case, the position of a laser dot. Then we're solving an optimization problem that minimizes a cost function, usually something that penalizes deviations from a desired trajectory, minimizing over lifted states and inputs, and enforcing that sequence of states and inputs has to be consistent with our linear dynamics, and that it starts from the right initial condition. And so so then we solve that, and we find the optimal sequence of inputs, and we apply that for one or sometimes more time steps before replanning this whole thing. So we're finding a sequence of inputs for a horizon of NH steps. I think in the example I'm about to show, we planned for like 20 steps or 30, something like that. But we only applied the first input in that sequence before replanning. And so what this linearity gets us here is that because we have a linear system, the constraint here is linear, this becomes a convex quadratic program. I didn't say this is a quadratic cost function. It makes this optimization problem convex, and then we can solve it using efficient convex solvers, and we have a global convergence guarantee because of that. So it lets us do this replanning MPC in real time at about, in this case, I think 40 hertz or so. So here's just some examples of trajectories that we followed using this MPC controller with the laser dot. And it's important to know that none of these trajectories were present in the training data set. The training data was just the laser moving all around. We didn't, train it to draw these shapes. We just built a model that could predict the input-output relationship and then used MPC to draw these shapes. And so if we compare that to doing the same linear MPC, but with the state space model trained on non-lifted data, we get much better results, especially far away from the hanging equilibrium point for the Koopman NPC system. So that, that was sort of the first example where we applied Koopman to a soft robot, and it was, a pretty simple system. But, we wanted to see next is, can we apply the same technique to a more capable soft robotic system, something that might be able to do pick and place task. So we built this soft robot arm that has a gripper at the end effector and has 3 independently controlled bending sections. So it's able to bend each segment independently. And we basically just applied the exact same technique, learned a Koopman operator from data to this system, but tried seeing the results of control when we put different payloads at the end effector. So here we have a simple reference trajectory of just lifting and then drawing, tracing out a circle. And for these 3 different payloads at the end effector, we see that for the small payload, it overshoots the trajectory, it lifts it too high. And for the heaviest payload, it doesn't lift it high enough. And so that shouldn't really be that surprising that the performance varies a lot with payload, given that soft robots, because of their compliance of their bodies, they deform a lot under loading. And so with a model, a data-driven model that doesn't take loading into account at all, we saw that we have like wide variability in our controllers when we have a payload. So that's obviously a problem if you want to build a robot that can actually like do tasks, because you don't want your robot's performance to be totally different depending on what it's trying to hand to you. So what we wanted to do is incorporate this loading into the model somehow. And the way to do that is we can actually just incorporate the payload into our set of measurements, and then also incorporate them into our basis functions. And then when we do that, what we get in the end is a linear model, but one that has this explicit dependence on the payload. So in practice, we measured the response of the system or collected data under random inputs for a set of different payloads at the end effector. Then lifted that and constructed a payload aware model, basically. So then we can compare. On the left side is the video I already showed, and on this side is the same test, but now it has the payload basically baked into its Koopman model. And what we'll see is that the version on the right has a much less spread between the 3 trajectories. They're much closer to the actual desired reference trajectory with the load incorporated into it. Yeah.
Are you still using just the lifting of the end effector here, or are you using all the markers on the thing and lifting everything? What is the logic?
Oh, yeah. No, we're using all, actually, we're using more than just the markers at the end effector. I don't remember. Shun might actually remember better than I do, because he was the one who set up this experiment. We put all the markers on there, but I think in the end we may have just used 3 sets of them. But we were lifting the position of more than just the end effector in this case. Yeah. Okay, let me go back to this. So this is an improvement, but of course, this only gets us about halfway there, because this controller assumes that the end effector is known. Like this controller, we told it whether it was holding a 25, 125, or 225, so it knew how to adjust its controller. But really, we want it to be able to adjust for that on its own without us having to tell it. And so here's another case where the linearity of the Koopman model comes in handy, because we could basically put a linear observer into the feedback loop that would, during operation, update an estimate of the payload at the end effector based on the learned dynamics. So here's an example for these 3 different payloads of as it moves the weight around, it can kind of figure out what the payload is. So then with those two things solved, so now we have a way of estimating the payloads online, and we have a way of, accounting for them. We were able to do perform a task that involved picking up an object of unknown mass, moving the arm around in order to estimate the mass of that object, and then placing that object in the cup corresponding to its mass, and then doing that repeatedly for a bunch of different objects. So in order to do this task successfully, it needed to be able to estimate the mass of the object within a 50-gram range. And then it needed to be able to position the end effector within a circle in the XY plane of radius, like 4 centimeters. Okay. So not, the precision that you have robots building your car doing, but for soft robots, at the time of this publication, as far as I know, this was the first demonstration of a soft trunk-like arm, like doing this type of automated pick and place with unknown objects type of task. Okay, so up until this point, I've basically just been saying like, okay, data-driven is great for soft robots. We can do everything by just learning it from data. And of course, there's also downsides to doing everything from purely data. And so one is that the more complex your system is, the larger your data requirements are in order to identify the good predictions for that system. And then again, like, your model is only based on what it has seen in its training data. So if you're trying to operate your system away from the dynamic range and the states that it has seen in its training data, you're probably not going to get good predictions unless you're lucky. So the question we had was, okay, like, could we construct more generalizable models with less data? So is there a way that we could still stay within this Koopman operator framework, but get better, more generalizable models with less data? And the answer is yeah, there's a way to do that. And it's basically taking this idea of residual modeling and applying it within the Koopman context. So what I can do is I can actually identify a lifted Koopman model by starting with a Koopman matrix that's based on a physics-based model, and then supplement it with a data-driven model that models the residual, so the modeling error of our physics-based model. And then we have a weighting factor that basically tells you how much to weight one of these over the other based on what it sees in the data. So let's see how I'm doing on time. Yeah, I can go through this. I may go a little fast, but the big ideas I think will be fine. We'll come across. So the first thing is, how do we construct a physics-based Koopman model, right? So far, I've said the way you construct a Koopman model is to do linear regression on data. But if you have a idealized dynamical model for your system to start with, maybe it's not super accurate because, you had to simplify things down to get this. But if you have this to start from, you can identify a Koopman matrix by, just like last time, identify a subspace in which you want to learn the Koopman operator. And then instead of doing linear regression on data, you can approximate the derivative of each of these basis functions by projecting that derivative onto each of your basis functions. So this is the inner product over a norm, and that serves to project psi I dot onto psi 1. And then you do that for all the basis functions. And when you do that, your dynamics of the lifted state can be represented by this matrix of these projection coefficients. So I'll call that here G bar, because in this case, this is the continuous version of the dynamics. And so we can get a discrete version of the Koopman operator, like what I've been using in the other parts of this work, by taking the matrix exponential of that. Okay, so that's the first part. And then to get the data-driven component, we collect data from the system. So we still have to collect data. And then we actually partition that data into two different sets. The first set is going to be used to identify a data-driven Koopman matrix the same way we did in all of the previous systems. So I just find the matrix that best describes the one-step transition between those lifted data points. But then what we do is we define our residual Koopman matrix to be the difference between the data-driven Koopman matrix and the physics-based one. And then we can use the rest of the data points to find the best weighting factor for the residual part of the Koopman matrix. So essentially, this gamma can be between 0 and 1. If it's equal to 0, your total model is just your physics-based component. And if it's 1, your total model ends up being just this empirical component. Okay. So if we apply this to a sort of simple simulated system like this, what we found, so this is a pendulum on a cart, it's two-dimensional dynamics, it's written here. And what we find is that if we plot so if we learn these Koopman models and then we do some validation trials and look at the prediction error, the root mean squared prediction error over our validation trial, the physics-based model doesn't change no matter how much training data we give it, which makes sense. It doesn't depend on the training data, right? It's just based on our physics-based model. Our data-driven model, however, it matters a lot how much training data we give it. It starts out with a really high error, but then as we give it more training data, that error falls. But then there's a little bit of, it's not a monotonic fall because depending on what random inputs you give it, you may get, data that's better or worse for predicting the behavior in our validation trial. So generally it drops as you add more data, but it kind of goes up and down. The combined model has the benefit of that when we have low data, it basically prioritizes the physics-based model. So we still get decent predictions. But then as we increase the data, we're able to have more consistent performance across different amounts of data. So it doesn't vary as much as the data-driven model does. So does this work on real systems? Yeah, it also works on real systems. So here's another soft robot arm that we made that has, again, it has 3 bending segments, but it has some structures in here that give it a little bit of a larger range of motion and payload capacity than the previous arm I showed. So I won't talk much about that design, but what we then see is, oh, this video always has problems. The physics-based Koopman model, when put into an MPC controller, let's see, does this work? Okay. This top video never likes to play all the way through. This is what, this is its performance in trajectory following. So there's clearly like, our physics-based model is not perfect. It's, we've made assumptions about the structure and the masses and everything of the links are probably not super accurate. So we get this tracking performance, whereas with the combined model where we had data to supplement it, we get much better tracking of the trajectory. Okay. I'm almost done. And then with this combined model, we can use it to do real life tasks like a pick and place task where the robot it picks up tools and sorts them into different bins in this case. We're not doing any estimation of the payload in this case. It's more just, we have a model and it's robust enough that we can get through disturbances. So it can still work even in the case of disturbances. And so another example of this is where we have a robot arm and we want it to draw the letter H on a dry erase board without knowing the exact position of the dry erase board. And the robot, it's using its body compliance to adapt to the constraint imposed by the board, and then using its controller to adapt to that. Okay, so this brings me to the end of the talk. In conclusion, the takeaway of the talk is basically that Koopman methods can be very helpful for modeling and controlling systems that are difficult to model and control otherwise, like soft robots. And so, the main advantages are that it gives you a way of constructing linear models or bilinear models for some systems, which helps you do real-time control. And then you can, incorporate other things into these systems like observers for loading. And because these are data-driven methods, you can apply it to a broad range of different types of systems. So just want to thank the many people who are involved in this work. Shun Fu is here, a new PhD grad from Michigan, and in my funding as well. So with that, I'll happy to take any other questions that you guys have.
I have two questions. One of them is a technical, and so you showed that pendulum example, but that's a 2-degree of freedom system. So why did you have only 2 equations there?
I know what you're talking about. It's because
This
the angle here is coupled to the displacement.
So there is some extra constraint on your system, or how?
There's not any extra constraint other than what's shown.
You show phi there. I guess that's x1 in your.
Oh, yeah, sorry. I guess this is, yeah, there's a label. Phi is x1, phi dot is x2.
And then you would need another coordinate to describe the position of that mass.
Yeah, it turns, you, in this case, you don't need another. Like, so you can have the position of this, but you can represent it with phi.
That's not true. How could that be true? It's a 2D. So they are 2 independent coordinates.
Well, we don't have any actuation at the pivot point. The only input is the F at the mass.
Yeah, but then it's again, there's 1 degree of freedom, which is the pendulum, the other is the X. Sometimes people eliminate that X because it's a cyclic coordinate, so they can get rid of that. But I don't see how did that happen.
Wait, so how do you say sometimes it's rid of how?
Cyclic coordinate. So basically that equation for the X, it becomes something like X double dot equal to blah, blah, blah. And you can put it into the other equation. So it's possible to eliminate that. I just wonder whether.
Oh, okay, that's what I did here. Yeah.
All right. The other question is less complicated. So in case of this high degree of freedom actuators, it looks really impressive. They can do these maneuvers. So it's and I understand that when you collect data, you can do whatever actuation you want. But what is the variables? What are the outputs you are collecting? So you only record the end, or what is the?
Yeah, it's not just the end. Oh wait, no, I'm going the wrong direction. But it is There's motion capture markers on this robot as well, so it's the position of basically points along the body, this point, and this point.
I see.
Yeah, so we don't have, embedded strain sensors or encoders in this example, so we're, for the, like, I didn't go over how we built our idealized physics-based model for the system, but basically what we do is we look at these, the physics-based model is in joint space. And so when we want to combine the data-driven part and the physics-based part, we have to map from motion capture marker space to joint space, and we make assumptions about constant curvature and things to do that. So there's lots of physical assumptions that we make in this case.
I think that's a really big strength of this research that, even though it's an infinite dimensional system, you're only tracking some finite inputs.
Right.
Yet you are able to do the control. I think that is pretty cool.
Yeah, and I mean, of course, this system's nice in that, all the soft robots, they're infinite dimensional, but practically speaking, like they're stiff enough that you see mostly like constant curvature segments, or you see sort of like more simplified geometry. So we could parameterize these infinite dimensional shapes with low dimensional approximations. And that's why these models can work. If I were to put motion capture markers on a string and fling it around, I think it would present a lot more challenges. Yeah. But I haven't tried.
I don't understand why there's like a Koopman operator associated to your physics-based portion that is not data-driven. I'm a little bit, so if you go back.
Sure.
A few slides on.
Yeah, I went quickly through that part. This part.
Yeah, yes, it's really just like a high-level question of what exactly is that Koopman operator, like you're weighing these different Koopman operators, one associated to this so-called residual and others.
Yeah.
To your physics-based model.
Yeah.
At a high level, what do each of these represent?
So it's basically like, we have an idealized physics-based model. It's nonlinear, and, it can give you predictions about your system. This is just our way of taking that idealized model and putting it in the Koopman context so that we can basically add it to the data-driven part, and they play together nicely, and together they're still linear.
How do you create a Koopman representation for that idealized system without having data?
Without data, yeah. So it's by projecting these dynamics, we know what these functions are, onto the space of our observable functions, of our basis functions.
Okay, yeah, it's magic to me. I mean,
Yeah, and I mean, it's not trivial to these are computing inner products in a function space. So that's for high dimensional spaces. That's like a nested integrals. So it's not trivial to compute these. So like baked in here, we're actually doing Monte Carlo integration, which is like a approximate way of computing those. So we're not actually computing those directly.
and a follow-up question on this, like, do you suspect that this like weighing of these like different Koopman operators, would you suspect that that would beat out some like learning framework that appends some like learned noise model to some like known system dynamics? Why not just learn the disturbances of your system while leveraging an existing model?
Yeah, I couldn't say that it would work, better necessarily. I mean, in fact, like this, the way it's written here, the data-driven component of the model, if you have really noisy data, doesn't help you very much. So I think you kind of look at your system, you look at like the quality of your data, and then, you can decide what's most suitable. But this gives you the linearity. Yeah. Okay, yeah. So I think he was first, and then Daphne, I'll get to you. Yeah, if there's time.
Curious about, so you, in the Koopman operator lets you bring this nonlinear things into this linear space, and you're able to like leverage that for control, right?
Mhm.
So I was wondering, is there a similar analogy for like state estimation? Like, could you just get the Koopman matrix and like design a Kalman filter from that, or does it break down in some way?
If so is there can you do state estimation?
Like a linear state estimation?
Yeah, so that's basically what we were doing in that payload estimation case. We were building a linear observer only of a subset of the state in that case, but yeah, when you have your linear model representation, you can build, those types of things into it. Yeah.
I was wondering if you've tried things beyond like position trajectory tracking, like impedance-based control or something where if you're gonna be interacting with humans, you might be concerned about that aspect as well.
Yeah, I haven't actually, so you mean like you'd actually be like gathering data of like reaction forces and things like that? Yeah, I haven't done any of that. I think it's a good idea. My, way of avoiding that is like, well, they're soft, so they take care of the reaction forces for us. But absolutely, I mean, you can construct a Koopman model from whatever data you want to include in your state. I just haven't done that. So good suggestion.
Some tasks I think that could be useful for too, possibly. So
Yeah. Okay, one last, yeah.
I have an implementation question for MPC. Since
Sure.
since you're using that to track a reference trajectory, that necessarily includes both a reference state component and a reference control aspect as well. Since you don't know the dynamics of your system, hence the Koopman operation, what are you doing to create that reference control input? Or are you just setting it to 0 and letting MPC tell you what to do?
So, I mean, we know the dynamics as far as our approximate model tells us what the dynamics are. So we're using that model in the MPC optimization problem to choose. So we're choosing a sequence of inputs that will generate a sequence of states that best follows the trajectory that we want to follow over that time interval. So we do have the Koopman model to help us do that.
So you're using that to help create the reference trajectory?
We're specifying the reference trajectory ahead of time.
So that's what I'm saying. You need to know what that reference trajectory is ahead of time.
Oh, yeah.
How are you creating that reference trajectory, like including the control aspect of that?
Well, so the reference trajectory is only specified for the state, or really the output. We don't even have to specify it for the full state. The input is, we don't define a reference input ahead of time. The MPC gives us the input that will best follow the reference output that we want. Yeah. All right, I think that's. Thank you, everybody.
Is not that complicated. I mean,
Anna, how are you? No, it's fine.
I have a question though.
Okay.
You were saying all this nice, calling all these paths. That they even have like SARF and.
Yeah, no, I don't have one of those. All been through the PC. Like.
I think I'm getting the project, I was like, but I just kept it all nonlinear, nonlinear result. Because I figured that there's so many constraints anyway.
Terms, you didn't have enough terms. Yeah.
That it wouldn't make any sense to me.
Yeah.
But for those examples too, like people often ask like,
I'm like, let's keep it like.
and
I guess I shouldn't discuss it with you. It's under review and then technically it's confidential, so I shouldn't know.
It's hitting us the constraint of not following probably, and it's just.
That's what they would say.
Stuff like.
Yeah.
The stuff that I do, but it's when it hits a constraint.
If you find a version on archive, then like.
yeah.
I don't know if that's what it's doing.
No, I think that is what it's doing, because it's, there's also the fact, like, the actual pressure control.
Yeah.
Is
Just send the request to my student directly.
Don't bother heading to the state. Just
Actually.
Yeah.
see how well that.
Yeah, I think that's right.
Archive now. So if it's on archive, I send them the archive.
Yeah, like, there's lots of tests where,
If it's not on the website, it's not in the public list, then I just treat it as confidential. I don't share it until it comes out.
yeah, I think that's a great idea. See if it can do it. And really, it's really, it's usually.
Not an M, but.
No, it was, yeah, that's my postdoc. We should have done both, yeah,
Every letter, so you can anticipate.
that's true.
Yeah.
Yeah. Like, I wanted to write like a message, but like the workspace is. The workspace to accuracy ratio is not. Yeah, that would be great, yeah, draw a picture, yeah.
Yeah, I know. Just results that look promising, but we're all gonna get run, literally the hub of just like. Yeah, let me mention that here. So I will certainly be doing for the experiments. Have a good weekend. So.
Trying to control the pressure, and there's like a PID loop in the pressure regulators to try to set these pressures.
Okay.
So that's one limitation, if we wanted to do like really dynamic swinging motions and like stuff like that.
Yeah.
We need a lot more data to get a good model, for that, so. Yeah, it was kind of sort of just from a practical standpoint, like we collected enough data that we could capture sort of dynamics within this frequency range, and we didn't quite be able to capture.
You'll have more inertial like things.
Yeah. I think so. It's, there's a Pandora's box to all this that like we could spend, and I have spent like many hours just like hitting my head against the wall in some of these experiments, but yeah, that's the reason. But if you notice, like early in the talk, it's like 8x speed, and then by the end it's 2x.
Yeah.
So we're like getting a little bit better in the range of motion.
Wait, I didn't know if it's a math thing of like because of using Koopman stuff, or it's just like a hardware.
It's a little bit of both. Yeah. Need more basis functions to represent higher order dynamics.
Cool, thanks. That was awesome.
Thank you, appreciate it. That wasn't boring, even though you've seen like most of them.
Yeah, I hadn't seen the hardware stuff.
There was some new stuff in
I
there.
missed your job talk because that was when I had a knot. Like, yeah, right. She came like a week before your job talk, so I was like, okay, probably not going to that, but yeah.
I appreciate your questions. Those are, yeah.
No, I have two questions.
Okay.
First is, on a day-to-day basis, you learn data on one robot. You talked about there's part-to-part variations.
Yeah.
But what about just day-to-day variations? You run it, you have to
Yeah.
recollect data, or does the same Koopman model work consistently over a long period
It
of time?
totally depends on the system. For these systems in this work, we actually didn't retrain day to day, like for that, for like the laser pointer robot, actually for all the robots, we would train it once and then use that for like weeks of testing.
Oh, okay. Yeah.
So yeah, there's definitely some, and part of that too is like the changes that the system is undergoing day to day
Yeah.
are small enough that like, and our error is high enough that like,
It's in the noise.
it's
so
in the
to speak.
noise, yeah, it's in the noise. So if we manage to get these things where we're getting like millimeter level precision, then we because we're kind of just in the ballpark, I think we don't worry.
Yeah. The second question is a technical question. I'm gonna try to phrase it the right way because it's not meant to be a critique. It's more an actual question. Koopman operator doesn't really play any role here, right? In the following sense, take a linear combinations of states, take quadratic monomials, stack them up. Fit that. Now I've got a model, it's ZK plus one is AZK. There's nothing Koopman about that idea, like, I get that the source of the inspiration is from Koopman, but there's nothing about the theory, like, if you told me that and you hadn't said Koopman at all, you said, I'm gonna take it, I'm gonna take the state, and I'm gonna take all quadratic monomials, I'm gonna fit a linear model to that. Boom, now I'm off and running, I can do linear MVC, you said I could do linear estimation, I did this observer, that's the real nugget of it, is that a fair statement?
I'd say, yeah, that's basically the nugget of it. I mean, I think that the thing is.
You will just control.
Yeah, you can control, but it's not efficient.
Lift and
You're doing nonlinear VC on lift displays.
now your lifted state is also predicting the future value of all those basis functions. So it's like,
Agreed. But the Koopman theory, like the fact that it's converging, if you've taken it,
Yeah.
like all that's,
I mean,
not relevant, at least for the practical application, that's what I'm
Yeah.
trying to, like, all the technical questions, is that, would you say, like, for what you're actually doing?
You can.
I mean, because once we get into the finite dimensional approximations, like, there's no guarantees of anything anyway.
Does it work? And if
Yeah.
those monomials that are quadratic aren't good, I could have used sines and cosines, and you're at some practical level
yeah.
trying to just figure out what's the best set of bases.
Exactly. You
Okay.
do that, that's right,
Okay,
yeah.
Right.
I mean, there are, so yeah, what I presented, yeah, you could basically just think of it that way. You don't have to spend your whole life reading up on all Koopman papers to understand what I've.
Yeah.
But in terms of like there's a lot of people trying to come up with better ways of like identifying basis functions to approximate it.
If you want to apply your states.
And for that, like notions of like spectral theory and Koopman eigenfunctions, I think come into play a little bit more in terms of like how you design the practical like tool to do that. But everything I've done here is just the vanilla versions, like. Yeah, I would like to implement some of that stuff in the future. Koopman, so it's just the body of work in Koopman has exploded so much since I started doing this stuff that like I can barely keep up with it. Just today, I like found a new paper on I just find the dictionary of basis functions and then go from there. And the more popular way to do it in literature now is to learn a set of basis functions using deep learning. So you do an autoencoder and then you decode to get your state.
The translation.
But there's another paper today that was like, oh,
This is always a state of the 50. You
find Koopman eigenfunctions from data that doesn't involve deep learning at all, but
try to the nonlinear.
it doesn't, you don't have to predefine a dictionary. So I better read this and figure out what they're doing.
So if you can use that here, because you don't use that as input to.
Yeah, so to your point, yeah, like.
Necessarily what you see, you can do your
That's why-
calculation method on nonlinear domain and you have a module that connects the two.
But you're totally right, like it's,
Then no.
you know.
That's the only level that I understand.
Yeah, you
It's
just,
not even you're starting from the states, you're starting from observables.
that's right. Yeah.
And then building monomials of the observables and saying that's what I'm gonna treat as the lifted state is quadratic functions of the monomials.
Yeah. Yeah.
Cool.
Thank you.
Yeah, it's like, I'm Pete, I'm not. Pete.
Thanks.
Oh.
Yeah. Yeah, they're good. I get to meet, more of the fact.
Santilia was building.
Oh, there's some chats on Zoom, but.
Oh, I didn't.
Oh, it's okay. There's late.
I think this is what I thought, so. Okay.
There was, I think, just one actual question. Let's see.
Okay, the ESC. Flight controller, what speaks, I guess it's the physics version of the PH4, yeah. So yes, it Polybro here. And then,
Yeah.
NVIDIA,
Streets.
gigabytes. It should be powerful enough, and I think they have also in all sense of the real sense depth scatter.